what I'm going to do, I thought I had this in here, but obviously not. I'm going to half make this up as I go along for some other notes that I got all this stuff from. Talk a little bit about, with regard to stepper motors, anti-resonance. So this is a little bit about what an implication of, or something that could go wrong with the use of stepper motor that you might need to be aware of. All steppers have natural anti-resonance frequency. Okay. Typically centered around the stepper motor's resonant frequency. Resonance actually helps the rotor helps rotate the rotor. Anti-resonance, on the other hand, impedes it. So that's the issue. What you get is an increase in audible motor noise if you get an anti-resonance, and an increase in motor vibration. Anti-resonant point will vary with, firstly, the application, secondly, the load. Typically, at lower speeds, (100 to 200 pulses per second, dps). Severe cases may cause missed steps. So right up front, when we talked about 1,000 steps to move 1,000 millimeters on that conveyor, and you're going to issue 1,000 steps and only move 998, we ain't going to be in position if we ain't got any feedback and do something about that. Yep. If we go back to our okay, right, simple permanent magnet motor that we've been talking about all along. If we draw time Okay. Angle of rotation. Well, I'm going to put a couple of dashed lines on there. At 90 degrees. (180 degrees). Okay. When a step is executed, the rotor shaft will undergo a period of time where ringing occurs before it finally settles at the energized state of pull. So if we imagine drawing a line on this diagram, the rotor is going to be moving through an angle, but it will experience that before it finally settles from where it started 0 degrees, where it is now, to where it settles and has moved through the 90-degree step angle that we've got there. It's naturally going to have some ringing. Okay. If we consider what could happen, so in terms of the next pulse happening here, we then go up there, so we hit 180 degrees again. We've got some ringing that will occur on that pulse. That is the rotor moving between there and there. So it takes a little while to settle. Like anything that's been moving, it's got some inertia before I'll bounce backwards and forwards before it'll actually settle. Okay. The issue comes where if the ringing is extreme, if the step time coincides with the oscillations. So if we do, in red, if I do something a bit more extreme in terms of the oscillations, we've still got some ringing, when the next step occurs in the middle of that ringing, it's possible then that we might miss that step, might not move away from that step. The rotor won't have time before the next step is applied, and we'll actually effectively miss a step. Alright? So in position sensitive applications like our conveyor, that could have severe consequences. So if we're talking about you moving a robot to a particular position to place a component onto a piece of kit and that put it in the wrong place, now that's the kind of implications we're talking about. And if you aren't using feedback, which was an advantage of stepper motors we talked about earlier, that we could do positional work without feedback, if you're not using feedback, you don't know that it's missed a step. Yeah? Now, in terms of solutions to that problem, half stepping is one way round it. And thinking logically, if you only move half the step, chances are your ringing's going to be a little less. You've always got one coil energized, so you're taking away the ringing that can occur, or at least reducing the ringing. So doing that half step will help that situation. What I'm going to finish off on, and I don't think is, what I'm going to finish off on is that if we go back to the idea of our initial application with regard to positioning. So, and this is a very simple, that was a very simple example of our conveyor. Operated by a stepper motor to move something from one position a precise distance, let's say 1,000 millimeters, to the next position. So if we knew that took 2,000 steps to do that, we'd send pulses to that motor, count the number of steps, and that would move, hopefully move from there to there consistently every time. The other issue, and without feedback. So we can get issues not having feedback anti-resonance. So if we're trying to move it at a certain speed and we get that anti-resonance, we can have an issue. Okay. The other thing is something causes that to stop halfway. No feedback means it doesn't know us halfway. It doesn't know where it is. So without feedback, you've got to consider that initially on startup, you've got to have some kind of sensor that says there's a home position for this piece of kit. And if something goes wrong halfway through a sequence, so if we're talking about a more complex robot that picks something up here, lifts it, turns, moves out and puts it down over there, if that stops halfway in between with no feedback, doesn't know where it is, the only thing you can do is have our return to home position, so it goes back, and then it knows how it can move from there to there, because it knows how many steps on each motor to get from there to there. Yeah? So that's the other implication of not having feedback. So many more complex applications that do use stepper motors will also include some form of feedback for that reason, because it gives you absolute control then instead of incremental. Incremental is we know how many steps it takes to go between now and there and we count them, but absolute includes some feedback so that we always know where it is between two limits. Yeah. Okay. That sort of concludes my theoretical part about stepper motors today. Yeah. So we'll have a look at what Chris has set up for us and see if we can see how these stepper motors work. On my YouTube channel, I actually recorded last year what we did with the stepper motor. So if you want, I'm not going to refilm that this year, but I'll put that up on the new on the site, linked into this lesson as well. So if you want to have a look at that, look back at that, you can. All right.